Okay, so welcome everyone to the last chapter of this book. We are going to be covering the theoretical part, and the main topic is going to be multiple testing. And the main objectives of this chapter is to identify the challenges of performing multiple hypothesis tests, and with that in mind, also to control the type 1 and type 2 errors. And then in the last part, we also take a look at another way to calculate p-values, not using theoretical distributions for the test statistic, but maybe another method that it seems to be more modern, more commonly used for big data sets, and that is going to be a case of resampling. So first, a little reminder of which were the main steps when we were working with hypothesis testing. So in that case, we had some data, and because that it constituted, it was like a sample from some population, and what we wanted to do is use such sample in order to make an inference about the population. So there is something that we want to test, and then we want to extrapolate if our prediction was right or not, but now for the whole population. So we start with some hypotheses. I am not going to read this part over here because I think the order is a little bit wrong, but in the next sub item, it has already been fixed. So I will only read this part over here. So this is an example of some null hypothesis, what is being labeled as H sub 0. And that would be that in some experiment where you have some control and some treatment group, our hypothesis is that the mean of some value, maybe, I don't know, like temperature for the people in that group, or pressure. If the mean is the control group or something that we are measuring, is the same also in the treatment group. So summarized as this, an equality of means. And usually what would be considered the alternative hypothesis, it tends to be just the negation of the null hypothesis. So the null hypothesis is like the default value that we assume in the world, but what we would really like to happen is for the null hypothesis to be false. So when it's some way of determining how can we say that with some degree of certainty, this hypothesis is not true. Okay. Over here, it's a little bit more in depth, the steps for the hypothesis testing. So as we saw in the previous example, we begin by defining some hypothesis, but then in order to get a sense of the strength of the evidence against such hypothesis, we make some test statistics. Then, using such test statistic and some information about the distribution of such a statistic, we can compute a p-value that would be a probability of observing that a test statistic value equal or more extreme than the observed one, but considering that the null hypothesis is true. And then in the last step, it would be decide to reject, well, if to reject or not the null hypothesis using the p-value that we obtained. So a little bit more in depth about these steps are, well, step 1, that is defining the hypothesis. It will depend on the investigation the one is doing. Then we do have a little bit more flexibility in this second step, because there are many t statistics that one could construct. At least in this chapter, we mainly see the two-sample statistic. So, sorry, the two-sample test. And for this specific null hypothesis that we considered in the previous example, the test statistic that we get that we define is as follows. We have also some approximation of the variance. And then yeah, and then what we see over here is it is called the null distribution. That is, what is the distribution of this statistic under the hypothesis as a null hypothesis is true. And we can see for this specific test statistic, these two sample tests, the form does look quite Gaussian, like normal, and that is in the case when these number of observations, they are quite large. So then using the distribution, using the null distribution over here, then we can get some, we can calculate some p-value, that is, calculate the probability of observing a value which is close to or more extreme than the actual observed one. So for example, over here, they consider the case that the D statistic, the observed one, happens to be 2.33. Then which region corresponds to more extreme cases of that? Well, we actually consider the absolute value of the observed value. And the more extreme cases would be this region to the right, like this part of the right tail, and also by symmetry, this region to the left. So the p-value would be the area under this curve, this little tail, and this one over here. And the main idea between these two steps, that is to make a t statistic, but then get some probability out of that statistic, is that there is not really a uniform, or maybe not uniform, but already set a scale for the t statistic that we will be referring to as a t-stat. So there is not really a scale for this value. So in order to get some range to work with, some consistent range, well, there is a p-value. The range is simply the interval from 0 to 1. So it does allow us for a little bit more interpretability, because now we're working with probabilities. Well, and this last part, this last step, that is, if we decide to reject the null hypothesis or not do it, well, that also depends on what type of threshold are we considering for the p-value. Sometimes it can be something like, if the p-value is smaller than 5%, then we do reject the null hypothesis. But in the book, they do mention that in more, let's say, precise sciences, something like physics, they say, this alpha value, this alpha threshold, it can be even something like 10 to the -9. So there is a lot of, well, not flexibility, but such threshold, it does depend quite a bit in the context. And in this part, they mention which are all of the possible cases with respect to the truth, not yet, the truth of the null hypothesis, if it is true or if it is false, and also the scenario if we happen to reject the null hypothesis or we fail to reject it. So in this case, that is when the null hypothesis is true and we reject it, that is called the type 1 error, and also it is labeled as the false positive, because there wasn't really a pattern in the data, but we are saying that there is. So it's like a false positive or a false discovery. There is also the type error rate, defined as a probability of incorrectly rejecting H0. And then there is also the type 2 error, and that happens in this scenario when the null hypothesis is false, but we do not reject it. So that would be, well, that is called a false negative, but a way to interpret it is like a pattern that was in the data, but that we failed to discover it. And then they simply define the power of the hypothesis test as a probability of correctly rejecting the null hypothesis. So the probability of actually making a valid discovery. And well, lastly, we're going to be taking a look also at this trade-off between the type 1 and type 2 error, because usually if you make one bigger, the other one, no, sorry, if you make one smaller, because that is what we want, then the other one tends to grow up. So it's another kind of trade-off that we come up with. So now in the general case of many null hypotheses being tested, the main challenge is as follows. This is a quote from the book. When testing a huge number of null hypotheses, we're bound to get some very small p-values by chance. And that is because, as we know, if some experiment, perhaps even a simple one as tossing a coin some number of times, if you repeat it many times, then it is pretty much guaranteed that in one of those instances, that is in one of those experiments, you get a value that has very low odds. So something like you toss a coin 10 times. Sorry, you toss a fair coin 10 times, and you get something like only tails or only heads. It has very low probability, but it can happen. And it is in a way bound to happen if you repeat the experiment a lot of time. So in that sense, that is what they mean that you get small p-values by chance. And in that sense, then there is a following problem, because in the case of only one hypothesis testing, we kind of had the idea that a small p-value was already good enough for rejecting the null hypothesis. However, if we can get a small p-value by chance, then are we not getting away with rejecting the null hypothesis for free? And yes, that we are getting a type 1 error almost guaranteed. So in a particular example, well, then how many type errors are we getting? For example, if we set a threshold for the alpha value, that is to decide when or not to reject the null hypothesis. If we set alpha to be 1%, then that means that there is a 1% chance to forcefully reject the null hypothesis if it happens to be true. So now in the case of having m number of null hypotheses, well, if there is a 1% chance of rejecting a single one of those null hypotheses, then we would expect something like m times 1% false rejections in total. That is m between, well, m times 0.01 number of false positives in this multiple testing scenario. So that's actually quite a lot if m happens to be big enough. So in that sense, we have encountered this problem that if you perform a lot of hypothesis testing, then you expect to get some type 1 error. So now the first goal that we're going to cover now is going to be, well, how can we limit the number of type 1 errors that we get when we are performing multiple testing? So with that in mind is that we define the family-wise error rate, and it is defined as the probability, over here, it is defined as the probability of committing at least one type 1 error. In this part, well, they're simply defining some scenarios, but the important variable over here is this one, B. And there is a number of false positives that we would get in this scenario of multiple testing. So formally, the family-wise error rate would be the probability that the number of false positives is greater or equal to 1. And then if we make some assumptions, like, for example, that each of the hypothesis testings has an alpha parameter, and that is the same alpha value for all of them, and that there is independence between these testings, then this formula can be simplified into this expression. And so we get that the family-wise error rate equals this value if the M tests are independent, and they all have the same alpha threshold. I think there is over here, yeah. Over here in the book, they show a graph. In the x-axis, we have the value M, that is the number of hypotheses or the number of tests that we are considering. And over here to the right, we have this expression that we found. For example, we see that if alpha equals 5%, that is the usual threshold, then once M becomes big enough, or maybe not even that big, for example, 10 over here, then such family-wise error rate, it's already how big? Let's see, so almost 0.5. So like a 50% chance of committing at least one type 1 error, that is of getting one false positive. But then if we limit alpha, that is we make it smaller, but obviously it's still positive. So something like a 0.1%, that is this line in blue, sorry, in purple. And now we do see that, for example, for the same value of number of hypotheses, so 10. Now, what is the family-wise error rate? Well, it's pretty small. I would think 0. I know, but almost 0. That is the main idea. It's almost 0. So now we are limiting the number of false positives that we would encounter in this multiple testing scenario. Okay, but that was using, sorry, this formula was using this, in this scenario, this hypothesis. So perhaps now we can see some more general cases. We do not require in these two first ones, over here and over here, for the test to be independent. So if we want to bound the family-wise error rate, there is actually a pretty easy way to do it. I do want to show the formula because it's pretty elegant. It is printed over here. And that is simply using this basic property of the probabilities or measures, that the probability of the union is smaller or equal to the sum of the individual probabilities. And using that type of bound, we get that if we limit each of the tests, or each of the hypothesis tests, for them to have an alpha value of alpha over M, then we can bound the family-wise error rate to be smaller or equal to alpha. So that is, we are making the probability of making one false positive, sorry, at least one false positive smaller than alpha. And that is simply by rescaling the alpha that we had for our individual testing, simply divided by a total amount of tests. And as I mentioned before, we are not really making assumptions about the independence of the tests or or some hypotheses about the null distributions and such. And a similar, I don't know, but perhaps before introducing the second one, they do mention in the book that, okay, so we do get this nice bound. It's pretty simple, simply divide by m. However, in our pursuit of making the total number of false positive very small, that is, of shrinking the number of type 1 errors, well, it has happened that this bound is not quite as good in the sense that we can still limit the number of type 1 errors, but also getting a smaller number of type 2 errors. That is, we can get a better balance of not having too many false positives, but still do not encountering the fact that maybe there was some hidden pattern in the data that we had enough evidence to declare, but we didn't. That is to also have a smaller number of type 2 errors or failed discoveries, let's call them. And in that sense is that this other method for controlling the family-wise error rate, it comes in handy. So the algorithm is pretty simple. So you have your m number of hypotheses. For each one of them, you can calculate the p-value. So you get p1, p2, and such. But then you can order such p-values. So now we have ordered them. And now that we have done that, then we can define L as the earliest point in this sequence such that this inequality holds. And then simply by rejecting each of these null hypotheses for which its respective p-value was smaller than the p-value corresponding to this index over here, that is to some position over here, then simply by doing that, we can not only control the number of type 1 errors, but now compared to this first correction, we also have a smaller amount of type 2 errors. And that is the same as having greater power. And power, we're going to define it in the next section. So in the book, they also mentioned two other methods. Basically, their use, it comes in handy when now you do have some information about the dependence of the testings. So as I mentioned, this procedure and this one over here, they both work independent of if the tests are independent or not. However, for these two cases, they do provide you with, again, better control of this family-wise error rate, but now having more information of the dependence of the tests, usually when they are indeed dependent between themselves. But it was saying in the notes of the previous cohort, so I didn't add it. Okay. So we already covered some basic ways for us to control the number of type 1 errors that we would get in multiple testing. Perhaps to have a little bit more clear this picture, we define the power as the number of false null hypotheses rejected. That is, false null hypothesis rejected. And I'm not sure if that would be the number of false positives. Well, okay. But let's say we find it as such, this expression. And the main idea is that as we have more and more tests, this expression is going to decrease. And what they mention in the book about why this is important is that in practice, when you consider many amount of tests, then we should be able to tolerate a few number of false positives, so that the number of so that we can make more discoveries. That is, if we limit to match the number if we limit to match the bound for the family-wise error rate, that is the number of false positives that we are willing to accept, then because the how do you say, the type 1 error is quite closely related to the type 2 error. As I said in the earlier section, there is a trade-off between them. If we make the type 1 error the number of type 1 errors too small, then that can make kind of big the number of type 2 errors. So in order to get a better balance, is that we can accept to get more false positives, but so that we do not miss some discoveries that were in the data, and that actually we had enough evidence to declare them, but we failed to. So in what follows, it's really just a better control of these type 1 and type 2 errors, so that we can accept some more false positives, but now we will get more discoveries. And they do this as follows. So instead of over here, we find the false discovery rate. It's going to be a Lucian term for controlling the amount of discoveries that we can make out of the data, the amount of positives, in the sense that this value over here, B, that it was actually the number of false positives. We do not longer want B to be small, that is, to commit no false positive, but we want it to be this expression small, that is, that the proportion of the false positives compared to the total of positives, that is, every time that we rejected a null hypothesis, we want this proportion to be quite small. So as I said earlier, we accept false positives so that we can get some more true discoveries. Well, this FTP, that is this false discovery proportion, as we saw, is defined as this, the number of false positives divided by the number of total positives. However, we do not have information about when there is a false positive. So really, the only thing that we can do is to try to estimate it. So this C is actually the expectancy. And then we define the false discovery rate as the expected value of this expression, the number of false positives divided by the total number of positives. So all of the rejections of the null hypothesis that we make in this multiple testing scenario. And they also mentioned that compared to the testing that we saw in the beginning, when we only have one hypothesis, over there is a common threshold of alpha. That is the probability of making a type 1 error, and that is simply the value 0.05. However, there is not a standard accepted threshold for controlling this false discovery proportion. Sorry, this false discovery rate. Then how can we really use a threshold? Well, that's going to depend in the context, and they mentioned that it will also depend on the dataset. So I guess that's where the expertise comes in handy when one is working in data science. Okay, so now our goal has changed because first it was, okay, so limit the number of type 1 errors. But now what we want to control is the proportion of type 1 errors or false positives in contrast to the total number of positives. That is this thing over here. We want to control it. So say that we want to control this in the sense of making this proportion, well, this expected proportion to be smaller or equal to some value q. We will define such q as a number between 0 and 1. And so there is an algorithm for, under certain scenarios, pretty much guaranteeing this. That is guaranteeing the proportion of false positives that we will get in this multiple testing. So again, it's pretty simple. So at first, we specify some level to control the false discovery rate. That is this Q value between 0 and 1. That is going to be an upper bound of this expected value. Then for each hypothesis, we have M of them. So for each one of those, we compute the actual p-values, p1 up to pm. And then, as in the previous algorithm, we order them. So this p sub 1 in parentheses is potentially different than this one. They are simply different indices for them. And now we find a specific index as the greatest among them, such that this inequality holds. And then what we do for the last step is we're going to reject each of the null hypotheses for which its respective p-value was smaller or equal than the p-value for this specific index that we got over here. And now there is a quote from the book that what have we achieved following this algorithm? It says, as long as the MP values are independent or mildly dependent, then this algorithm guarantees that the false discovery rate is going to be smaller or equal to Q. And in more layman terms, they mention in the previous cohort that on average, then no more than a fraction of Q of the rejected null hypothesis happen to be false positives. And I didn't get quite this part about when are the p-values independent of each other. I would suppose that they mean the tests to be independent, because the p-values, I mean, they are probabilities, and probabilities can't be independent. Maybe, no, the distributions. Maybe the random variables associated to the null distributions for each one of the hypotheses. So I am not quite sure what they mean for p-values to be independent. And in what follows, well, Federica, who was the one who wrote this part, I only make a few corrections. There is a comment. Let's see, Derek says, it may be the case that the proof of the Benjamin-Hochberg procedure is easier if the underlying variables are independent. If the underlying variables, maybe the ones from the population. Yes. Okay. Well, as I was saying, what follows in this part is really just the R application of what we have already been seeing in this part. So I'm going to skip it because we usually don't cover the lab. Well, what follows is a resampling approach, but I wanted to cover that part still in the next meeting, because the next meeting, well, it's going to be the last one. For that one, well, I just wanted to do the resampling approach for the beginning and then cover some of the exercises, because I mean, there happens to be enough time. I will just provide a little bit of context for why that was the case. And the main idea is that we're actually making some strong assumption usually when we're calculating the p-value. So let me come back to some over here, for example, because when we're performing in this specific scenario, we have this null hypothesis, and we're using some specific hypothesis testing. In this case, it's a two-sample test. Well, for this case, under certain conditions, so for example, something like the number of observations in the training sample and the number of observations in the control group, they're big enough, then it happens that this value follows approximately a normal distribution with parameters 0 as the mean and 1 as standard deviation. And such distribution of this test statistic, well, that is called the null distribution when you're assuming this to be true. However, in this case, we know what is the null distribution. It is simply a normal one, but sometimes it may be the case that we do not know what is the distribution. And also it can be the case that the number of observations is not big enough. So for any of those two scenarios, is that there's going to be an approximation of what is the null distribution, that is of the distribution of this under this assumption. And once that we approximate such distribution, then we can calculate the p-value, because it's simply going to be a certain area. No, it's going to be an area under a certain region over that approximate distribution that we are going to make. So that's amazing. Well, we will be ending over here, so I will put this in the chat.